Okay, good day, grade 11s. I trust that you are well. This lesson is basically on our first topic for the year, which is exponents and surds, which is a very exciting topic. And of course, it forms part of algebra and it will link to simplification of algebraic expressions and so forth. But before we continue, exponents is not a new topic. It's something that we looked at in grade 8 and grade 9 in high school and also in grade 10. And in grade 11, we just extend that a bit and we look at, of course, slightly more interesting examples and including surds as well. So of course, the surds has to do with your nth root, whether it's your square root, your cube root, your fourth root, your fifth root, and the like. So what I'm going to do first, before I look at very interesting grade 11 examples that are on the standard of both the DBE and IB questions, it's mostly exam focused questions. I'd like to just to do a quick recap on all the laws of exponents. So I'm going to look at the laws of exponents as well as the exponential definitions, not in any particular order, so I'll just be discussing it. But I think where we should start first is to understand what an exponent is. So an exponent is basically something like this: a raised to the power of n, and that's how we read it: a raised to the exponent n. And the exponent actually tells us how many times the base is being repeated. So in this case, the base is being repeated n times. So it's a times a times a, and of course it depends on what that value of n was. So for example, if I write 2 raised to the power of 3 as an expression, the mistake I see learners make is that they will say that this means 2 times 3, and that is absolutely incorrect. 2 cubed actually means that 2, which is the base, is being repeated 3 times. So that's 2 times 2 times 2 times 2 times 2. And of course, 2 times 2 is 4, 4 times 2 is 8, right? That's basically the first definition. But where we should start off with regards to the laws, is the first law of exponents. So let's look at that. And that is, so again, not in any particular order, but let's just look at this first law: a raised to the power of m times a raised to the power of n. And I'm going to be a bit quick on this because, again, this is just a recap from grade 8, 9, and 10. So in this case, I'm multiplying and the bases are the same. When you multiply and the bases are the same, we keep the common base. In this case, the common base is a, and we add the exponents together. So it's going to be, the product would be a raised to the power of m plus n. Secondly, let's say we are dividing, so we have a raised to the power of m divided by a raised to the power of n. And by the way, division is the same thing as a fraction. In a fraction, the numerator is being divided by the denominator. So you could also look at this expression as a raised to the power of m over a raised to the power of n. It's the exact same thing. It's a raised to the power of m divided by a raised to the power of n. And let's see what this is equal to. In this case, we are dividing and the bases are the same. The common base is a, so my quotient will have the common base of a, and I'll subtract the exponent. Always start with the first exponent minus the second exponent. The same case with the fraction: the exponent of the numerator minus the exponent of the denominator. Then we can look at the further power rule of exponents, which basically states that a raised to the power of m or raised to the further power of n. What do? We multiply the exponents together. And let's say we are multiplying different expressions inside the brackets that have some, that's not equal to, but we multiplying different exponents inside the brackets that have exponents. So for example, if we have a raised to the power of m times, remember, I'm not adding, I'm not subtracting, I'm multiplying what's inside the brackets, b raised to the power of, let's say, n, or raised to the further power of t. So basically, the further power has to have a chance to be multiplied to the exponents of every base inside the brackets. So what do we have? We have a raised to the power of m t, which basically means m times t, times b raised to the power of nt. And that is what I have. Then there's other exponential definitions, like for example, if I have a raised to the power of 0, I'm going to try to go through as much as I can now, but as we go through different examples, you'll see we'll be able to apply them. So any value raised to the power of 0 is equal to 1, except for 0, of course. A cannot be 0 for obvious reasons because a raised to the power of 0 is undefined. So there is some restrictions here and there, but I'm just going through everything assuming that, of course, it meets the proper requirements and does not contradict any restrictions. Thereafter, we can look at the mth root. This is something you looked at in grade 10. The mth root of a raised to the power of n, which is equal to a raised to the power of n over n. We also looked at a raised to the negative exponent, and of course your final answer, and this is very important, your final answer in any expression should not be or should not have a negative exponent. So how do we rewrite a raised to the power of negative n such that we have a positive exponent? We can write that as 1 over a raised to the power of n. And you'll pick up on many examples. Using this application, we can actually see, let's say for example, we have 1 over a raised to the power of negative n. That is equal to a raised to the power of positive n. And you can do the maths behind it. It's basically 1 over 1 divided by 1 over a raised to the power of n. And how do we divide fractions? We keep change flip. Again, this is just a quick recap of grade 8 and 9. I'm not going to spend too much time on this because you can go back to that content. I'm just looking at as much as I can at the moment. We can also look at, for example, applying what we know about a raised to the power of negative n. And this is quite important in grade 11, so bear this in mind. Let's say we have a fraction raised to a negative exponent. So let's say we have a over b, or raised to the exponent negative n. This is equal to the reciprocal of the fraction. Reciprocal basically meaning that we flip the numerator and the denominator. The numerator becomes the new denominator and the denominator becomes the new numerator. But now, instead of raising it to negative n, because we found the reciprocal, we flipped it around, it's raised to positive n. Very, very fascinating. And we can apply this to different examples as well. And so those are some of the definitions of exponents. Of course, they are more, like for example, if I have a raised to the power, let's say n, I'm just using variables, b raised to the power of m, or raised to the further power of t. I basically take the further power and I raise it to the numerator, and I take the further power and I raise it to the denominator. And again, it stems from the further power rule of exponents. So what will this be equal to? What is the final expression? It should be a raised to the power of n times t over b raised to the power of m times t. So those are some of the exponential laws. Now in grade 11, we will look at, or we will rather focus more on the surds. Of course, we need to know the exponents, our laws and definitions of exponents, but let's just look at some of the surd laws, which I find to be quite interesting. Okay, so let's just get a new screen. Right. So I am going to slow down the pace once we start with the examples, but of course a quick recap on these laws are quite important. So let's look at some of the surd laws. Right, again, not in any particular order, but let's look at the first one. Right, let's say I have the nth root of a, right, times the nth root of b. And by the way, there is a restriction for n, right? And what will that restriction be? So if you said the restriction should be that n should be greater than or equal to 2, where n is every natural number thereafter, that makes more sense because there is no such thing as the 1th root or the 0 root or the negative 1th root or the negative 2 root. It's always the square root. There's an invisible 2 for the square root. So the square root actually looks like this. It's just that we express the square root as the square root surd sign. But there's actually an invisible 2. And thereafter we get the cube root, then we get the 4th root, the 5th root, the 6th root, and so forth. So let's say we have the nth root, whatever n may be, of course, according to our restrictions. The nth root of a times the nth root of b is equal to the nth root of ab, right? So you multiply the a and the b, and it's all under the radical sign, under the square root, or the nth root, right? Next, let's look at, let's say we have the nth root of a over the nth root of b. That's equal to the nth root of the entire fraction a over b, right? And now let's say we have I'm trying to recall the laws as well. Let's say we have the mth root of the nth root of a. So let me read that again. The mth root of the nth root of a is just basically equal to the mnth root of a. And I know I'm going a bit on a tangent here, on a side note, but let's just look, why is that the case? Why is the mth root of the nth root of a equal to the mnth root of a? So let's just take this expression, right? The mth root of the nth root of a. First things first, let's just deal with what's inside the radical sign, what's inside the mth root, which is the nth root of a. That's going to be equal to the mth root of a raised to the power. There's an invisible exponent of 1 of the a, so it's the mth root of a raised to the power of 1 over m. Over n, right? Because we have this n here. And remember, this entire expression has an invisible exponent of 1. So just imagine that the base is a raised to the power of 1 over n, and there's an invisible exponent of 1. So what is this equal to? This, we can apply the further power law again, which is a raised to the power of 1 over n, or raised to the further power of the exponent, which is 1 over m. And now how do we deal with the further power? We take the exponent that is outside the further power and we multiply it to the exponent. And that is equal to a raised to the power of 1 over n times 1 over m. How do we multiply fractions? Top of the top, bottom of the bottom. So that gives me a raised to the power of 1 times 1 is 1 over n times m is mn. You know, the commutative property, I can swap it around perfectly fine. And again, using what we know, that the mth root of a raised to the power of n is equal to a raised to the power of n over m, we can rewrite this as the mnth root of a raised to the power of 1, as an invisible 1. And that is the reason why we have this third law. And lastly, let's say we have, let's use brackets here. Let me get this right. Let's say we have the mth root of a or raised to the power of n. So you can again just do the definition and you can write this as a raised to the power of 1 over m. And you take the further power n and you multiply it to that fraction. At the end of the day, you can rewrite it as the mth root of a raised to the power of n, right? So the further power actually can be multiplied to the exponent of a that is inside to the mth root. Very fascinating. Now, what we're going to do now, we're going to use everything that I just recapped, all the laws of exponents and surds that we looked at, and we are going to apply it to different examples. So before we continue, how are we going to approach this? I'm going to write the question. I recommend that you press pause on the video and you attempt it yourself, and thereafter we can mark it together, because that's the best way to learn math. You cannot watch math, you have to practice math and actually apply it on yourself. So please do that. I'm going to write the question, press pause, work on it yourself, and thereafter you can press play and we can look at the solution together and you can mark your work if you need to, right? Now let's look at example number 1. Again, these are IB level questions and it's good practice as well. So I'm going to write it out. The first question, question 1, right? We need to express 2 over the square root of 3 minus the square root of 3 over 2 in the form of the square root of a over b, where b is not equal to 0. Very important restriction, right? Because of course the denominator cannot be 0, else it's undefined. And the square root of a is a surd, right? Which makes sense because a is inside the radical square root. So let's look at this very interesting example, and thereafter we will discuss the solution. So this example has to do with adding and subtracting fractions as well as rationalizing the denominator, which is something uh, we discussed in class as well. So very quickly, press pause on the video and attempt this question. Okay, so I assume you have worked out the solution, and your final answer should be the square root of something over b. Of course, b cannot be 0. Whatever your answer is, pretty sure b cannot be 0. Now let's look into this. We have 2 over the square root of 3 minus the square root of 3 over 2. I wanted to start off with this example because this example deals with rationalizing the denominator. Okay, and I started off with this is because this is something that is introduced in grade 11 and not in grade 10. Rationalizing the denominator basically means that we needed to get rid of the nth root in the denominator. So let's say you have an answer like your final answer is 1 over the square root of 2, which looks perfectly fine. But the problem is that we have a square root in the denominator. It's fine if the square root is in the numerator, but once you see that there's a square root in the denominator, that poses a problem. So how do we get rid of the square root? What we need to do is multiply this entire fraction by 1 so that we do not change the value. But how do we write 1? We write 1 as the square root of 2 over the square root of 2, because we do know that any value divided by itself is equal to 1, except for 0, because 0 divided by 0 is undefined. But any other number divided by itself, whether it's a fraction divided by a fraction by itself, it's always equal to 1. So now how do we multiply fractions? Top of the top, bottom of the bottom. 1 times the square root of 2 is the square root of 2. Square root of 2 times the square root of 2 is equal to 2. That's also something that's fascinating, is that the square root of a all squared is equal to the absolute value of a. What do I mean by absolute value? It means that a has to be positive, right? A has to be a positive amount, right? So a cannot be negative, right? Now back to our particular question, right? Before we start rationalizing the denominator, let's just add these two fractions together. Let's ask ourselves, what is the lowest common denominator? Because when we add or subtract fractions, we have to look for the lowest common denominator. So what's the lowest common denominator between the square root of 3 and 2, right? And the lowest common denominator should be 2 square root 3. So my LCD should be 2 times the square root of 3. So if I look at this fraction, I need to multiply by 1 to not change the value. But how can I get, or what must I multiply the square root of 3 by to give me the LCD of 2 square root 3? And the obvious response would be multiplied by 2, right? So I multiply this entire fraction by 1, so that's 2 over 2 times 2 square root 3 minus the square root of 3 over 2. Now what do I need to multiply 2 by to give me the LCD of 2 square root 3? And yes, the obvious response should be multiplied by the square root of 3 over the square root of 3. Now I can multiply the fractions top of the top, bottom of the bottom. 2 times 2 is 4 over 2 times the square root of 3 is 2 square root 3 minus square root of 3 times square root of 3 is square root of 3 all squared, which is positive 3 over 2 square root 3. Now I have a fraction and I have common denominators. So we know how to add or subtract fractions. A over c plus b over c is equal to a plus b over the common denominator of c. So that's the reason why we found the LCD, so that we can get common denominators. It's always best to work with the lowest common denominator. So now we have 4 minus 3 over 2 square root 3, which is equal to 1 over 2 square root 3. Now this is perfectly fine as a final answer. However, we cannot leave it like this. Why? Because there's a square root in the denominator. So we have to rationalize the denominator. How do I know this? Because they also said that the final answer should be in the form of square root of a over b. And it's good practice and it's reasonable to write your final answer with a rationalized denominator. So how do I get rid of the square root of 3? What I'm going to do is I'm going to multiply this entire fraction by the square root of 3 over the square root of 3. That's equal to 1 times the square root of 3 is the square root of 3 over square root of 3 times the square root of 3 is 3. So it's 2 times 3. So my final answer is the square root of 3 over 6. 2 times 3 is 6. And that is my final answer. So I know I started off with quite a unique question 1 because I wanted to discuss rationalizing the denominator, a concept that is introduced in grade 11. But let's go back to something slightly more basic, right? So let's look at an example that actually applies exponents and surds. I think that will be quite interesting. So I'm going to do 2 examples on simplification of exponents and surds. So let's look into that, right? Let's look into that. Okay, so let's look at the next example. We're on example 2, right? Or question 2. We are required to simplify, and of course, most of the time they'll say simplify without the use of a calculator, right? So we're simplifying without the use of a calculator. So what do we have? We have the square root of a half times 0.5 raised to the power of x minus 1 times the square root of 2 raised to the power of 2x minus 1. And we are required to simplify this expression. Okay, so the first things first, if I look inside the square root, I can see a half. I can rewrite a half as an exponent, which will be the square root of 2 raised to the power of negative 1. What law of exponents am I applying? On the side note, I'm applying a raised to the power of negative n is equal to a raised to the power of uh, 1, sorry, what am I doing? It's equal to 1 over a raised to the power of n, positive n. So just imagine we were given 1 over a raised to the power of n, and I'm rewriting it such that it is a raised to the power of negative n. That's what I did to the half inside the radical sign. Times, a half can be written as 1 over 2, because we do know 0.5 is 1 over 2, it's a rational number, raised to the power of x minus 1 times 2 raised to the power of a half, or raised to the power of 2x minus 1. Right, now I have the square root of 2 raised to the power of negative n. How do I work that out? It's 2 raised to the power of negative 1 over 2. Why? I'm applying the law that states, right now on the side, I'm just going to just recap on some of the laws here as well. The nth root of a raised to the power of n is equal to a raised to the power of n over n. So that's what I'm applying in this situation. So I have times, so I have 2 raised to the power of negative 1 over 2. And in this case, I can rewrite a half as 2 raised to the power of negative 1, or raised to the power of x minus 1, times 2 raised to the power of half, or raised to the power of 2x minus 1. Now, the point, I just left that as such because I want to explain this in more clearer detail. So I have 2 raised to the power of a half times 2 raised to the power of negative n times, 2 raised to the power of negative n raised to the power of x minus 1. Now again, what law of exponents am I applying? I'm applying the further power law. A raised to the power of m, or raised to the further power of n, a raised to the power of m, or raised to the further power of n is equal to a raised to the power of mn. So I'm going to take the further power and I'm going to multiply it to the exponent. The common mistake I see a lot of learners make is that they write the final expression as 2 raised to the power of negative nx minus 1, and that's not correct. The negative n is being multiplied to this entire expression. So it's negative n, you use the distributive property, negative n times x, which is negative 1x, sorry, negative 1 times x, which is negative 1x, and negative 1 times negative 1, which is positive 1. So I have 2 raised to the power of negative x plus 1, and the same applies to the half. It's 2 raised to the power of a half times 2x is just x, A half times -1 is negative a half. Now what law of exponents am I going to apply? Now I'm going to apply law 1, something you learned in grade 8 and grade 9 and 10. When multiplying and the bases are the same, you keep the common base, in this case the common base is 2, and you add the exponents together. So I just add all my exponents together, right? So at this point, what do I have? I have negative a half minus a half is -1. -1 plus 1 is 0. Now I have negative 1x plus 1x. They are like terms. They both share the same variable and the same exponent, so they like terms, which is also 0. So I have 2 raised to the power of 0, and my final answer is 1. And that is example 2. Okay, let's quickly move on to example 3. Again, I hope you are pressing pause and you are attempting it before I discuss the solution with you. So let's look at the next example. Okay, let's look at the next example now. Example or question 3. Right, again, we are required to simplify. We have the square root of 20x raised to the power 5 times the square root of 10x plus the square root of 2x raised to the power 6 all over the square root of 2 times x cubed. Okay, so looking at this question, very quickly press pause, attempt it, and then we will discuss it. Right. Okay, so looking at this question, right, or looking at this entire expression, this monomial, this entire thing is a monomial. Let's first deal with the numerator, because in maths we do things part by part, right? We look at the numerator and we try to simplify the numerator if we can. Then we look at the denominator and we try to simplify the denominator if we can. So looking at the numerator, in the numerator itself, I know this entire expression is a monomial, but just looking at the numerator, just imagine the denominator is not here for now. Just look at the numerator. It's a binomial, right? And if I look at the first term of that binomial, I can apply one of the laws of Surds, which states that the nth root of a times the nth root of b is equal to the nth root of a times b. If you're not too sure, go back to the first few minutes of this video and I recapped that law. So we have the square root of 20x raised to the power 5 times 10x. So 20 times 10 is 200, and x raised to the power 5 times x raised to the invisible exponent of 1 is x raised to the power of 6, plus the square root of 2x raised to the power of 6 over the square root of 2 times x cubed. Now again, in maths, a lot of learners try to rush and do as many simplifications in one step. Why not just do step by step so that it avoids making any unnecessary mistakes, right? So in this case, what am I going to do? I'm going to rewrite the square root of 200 x raised to the power 6. Now sort of the reverse of that law. I'm going to split that up into the square root of 200 times the square root of x raised to the power 6 plus the square root of 2 times the square root of x raised to the power 6 all over the square root of 2 times x raised to the power 3, right? Now, whenever you see a numerical base that looks quite large and a bit unusual, what do? We rewrite them as a product of their prime factors, and this is where your calculator comes into play. So with the use of calculator, just enter 200, shift fact. Now you could use the ladder method or you could use the tree method to rewrite a number as a product of its prime factors using prime factorization. However, you are in grade 11, you have a calculator, let's save some time. 200 equal to shift fact. I have the square root of 2 cubed times 5 raised to the power of 2, 5 squared, times the square root of x raised to the power of 6. I'm going to use the law that states, or the definition, the mth root of a raised to the power of n is equal to a raised to the power of n over m. So I can rewrite the surd uh, as a base with an exponent that has a rational number as the exponent, which is x raised to the power of 6 divided by 2, which is 3, plus the square root of 2 times x raised to the power of 3. 6 divided by 2 is 3. There's an invisible 2 in front of the square root over the square root of 2 times x cubed, right? Right, now I might need some space, so let's move on here. Right, so I'm going to continue my solution here. This is equal to, now I have, let's look into this carefully. I have the square root of 2 cubed. Now, just be very deliberate here. 2 cubed can be rewritten as 2 squared times 2 raised to the power of 1 using the first law of exponents. Why on earth am I doing this? Why am I splitting this as 2 squared times 2 raised to the power of 1? Because there's a square and there's a square root. So I want to get rid of that square root. So I'm going to be very deliberate on how I rewrite the 2 cubed. I'll rewrite it as 2 squared times 2 times 2, times 5 squared. Right, again, I'm taking my sweet time. There's no need to rush and get the final solution. As long as you do it part by part, it's perfectly fine. I notice that many learners, they will simplify and do a lot of things in one step, and as a result, that causes a lot of unnecessary mathematical mistakes. So in this case, how can I rewrite the square root of 2 squared times 2 times 5 squared? And by the way, I'm being very deliberate because I notice that there's a plus in the numerator. If there's a plus in the numerator, what comes to mind is possibly factorization. I might be required to factorize by taking out a common factor, or maybe another type of factorization, but in this case, it has to be taken out the common factor. So this will simplify to the square root. Again, I'm going to work on this step by step, so you can see I'm not going to skip any steps. The square root of 2 squared times, let's start off with the 5, the square root of 5 squared times the square root of 2 times x cubed plus the square root of 2 times x cubed all over the denominator of the square root of 2 times x cubed. Now, of course, the square root of 2 squared is 2 times 5. The square root and the square, they undo each other, so that's the reason why I deliberately rewrote 2 cubed as 2 squared times 2. The square root and the square, they undo each other, so I'm left with that positive integer, or that positive value, times the square root of 2 times x cubed plus the square root of 2 times x cubed over the square root of 2 times x cubed, right? And that's equal to 10 square root of 2 times x raised to the power 3 plus the square root of 2 times x raised to the power 3 over the square root of 2 times x raised to the power 3. And now if I look at the numerator, I can actually see that these two are like terms, right? So you can add the like terms together, or if you cannot see that, why not just factor out the common factor? As I said, this is a binomial, so between the first term, which is 10 square root 2 times x cubed, and the second term, which is the square root of 2 times x cubed, what is the common factor? And the common factor, the highest common factor, should be the square root of 2 times x cubed. So I'm going to take the first term and I'm going to divide it by the common factor. I'll be left with 10. Plus, I'm going to take the second term, I'm going to divide it by the common factor. I'm left with 1. Because you do know the square root of 2 times x cubed divided by the square root of 2 times x cubed is 1. All over the denominator of the square root of 2 times x cubed. Now what do you notice? You notice that the square root of 2 will divide off with the square root of 2. X cubed divided by x cubed is 1. Right? So this divides 1 time, and I'm left with 1 times, in brackets, x plus 1 over 1 times 1, which is 1. And all I can write is 10 plus 1, which is 11. So my final answer gives us a nice whole number of 11. Okay, good. Right. Now, that being said, let's quickly discuss the next solution or the next question as well. Okay, so let's just take part of this question out. Yeah, I think that should have, okay, there's just slightly more parts that I need to erase. Right, okay, I think that should do it now. So now we can officially move on to our next question. Right, very exciting. Let's look at the next question. Okay. My goal is to try to do as many questions as I can, just so that you have a reference and, of course, a step-by-step guide on how to do this. Right. So let's look at question 3. Right. I believe this is the third question, if I'm not mistaken. We're required to simplify. I think this is the fourth or the third, but just bear with me. It's the next question. Right. We're required to simplify uh, the next step. Right. The next step. So I have the square. This is a very nice question. Again, try to press pause and attempt it yourself. I have the square root of b plus the square root of 2b minus 1 times the square root of b minus the square root of 2b minus 1. Right? So this is really interesting because although this seems very, very complicated, right? It's just a square root, and whatever is inside, it's been multiplied by another square root with something inside it. So what comes to mind? The first law of surds, the nth root of a times the nth root of b, which is equal to the nth root of a times b. So whatever is inside the first nth root must be multiplied to whatever is inside the second nth root. Right? So what do we have? We have the square root of whatever is inside here, which is b plus the square root of 2b minus 1. It's being multiplied to whatever is inside the second surd, which is b minus the square root of 2b minus 1. Right, very interesting. Now, if I look at the first expression, what was inside here? It was a binomial, and I can see that there's something very fascinating here. In the first term, in the first brackets, I have a b. In the first term, in the second brackets, there's a b. It's identical. Thereafter, if I look at it carefully, the second term, which is the square root of 2b minus 1, it's identical to the square root of, is identical to the second term in the second brackets, which is the square root of 2b minus 1. It looks almost identical. These two binomials are being multiplied. What is the difference? The difference is the plus and the minus. Now we need to find the product. All right, let me get this right. It's the product of the sum and difference of two binomials that have the same terms, right? It's only the sum and difference that the plus and the minus that creates the difference. So how do we do that? We could use FOIL, which is a very long, tedious process, but it's the sum and difference of two squares. So I'm going to say b squared. I'm going to square the first term minus square the second term. Right? So if I gave you the expression b squared minus, in brackets, the square root of 2b minus 1 all squared, and I asked you to factorize that, it will be the sum and difference of, it will be the difference, not the sum, it will be the difference of two squares. And in this case, we can just simplify this, which is going to be the square root of b squared minus the square root and the square, they will undo each other. So this expression is being subtracted, so it's going to be 2b minus 1. Please do not forget to include the brackets. A lot of learners forget to include the brackets, and that's quite dangerous. So now I have the square root of b squared minus. Now remember, when you are subtracting an expression, it's actually, think about it as a negative 1 in front of the brackets. So we're going to distribute the negative 1 into the brackets. So we have negative 1 times 2b, which is minus 2b, negative 1 times negative 1, which is positive 1. Now I can see that there's a trinomial, and whenever I see a trinomial in the standard form of ax squared plus bx plus c, what immediately comes to my mind? What comes to my mind is factorizing a trinomial, right? So I'm going to use the window method, which in my opinion is the easiest way to factorize a trinomial. So I have the first term of the trinomial, which is b squared, the last term, which is 1, and b squared is on top of the first window, positive 1 is on top of the second window, and in between I have the middle term, which is negative 2b. So how do I get b squared, right? What two values multiplied to each other gives me b squared? Of course, it'll be b and b. What two values multiplied to each other gives me 1? It's going to be 1 and 1. But when I cross multiply, 1 times b gives me 1b, 1 times b gives me 1b, 1b plus 1b gives me 2b. And I need the sum of the product when I um, cross multiply to give me negative b. So what am I going to do? Instead of stating 1 times 1 gives me positive 1, I'm going to write this as negative 1 times negative 1 gives me positive 1, because we do know a negative times a negative is positive. So negative 1 times b is negative 1b, negative 1 times b is negative 1b. So negative 1b minus 1b is negative 11b. Sorry, negative 11, negative 2b. They are like terms. So my factors are b minus 1 times b minus 1. And of course, we multiply these two together, so that's the same as b minus 1 all squared. It's the square of a binomial. So now I have the square root of b minus 1 all squared. So again, the square root and the square, they undo each other. Think about it as they undo each other, and I'm left with b minus 1. And I cannot simplify that any further. My final answer is b minus 1. Okay, so again, this was a very interesting question. Okay, let's look at the next question. Right? Now I'm going to move on to solving exponential equations, which is very exciting. Right? Solving exponential equations. Let's look into it. Okay, so right before we start off with this, well, I won't say new topic, but it still forms part of exponents and surds. But before we look at solving exponential equations, right, I'm just going to quickly drink some water. Right, okay. So exponential equations, right, let's start off. Exponential equations. We know what an equation is. An equation is an expression or an algebraic expression equal to another expression or algebraic expression. And we need to satisfy the equation such that the left-hand side is always equal to the right-hand side of the equation, right? We looked at linear equations in great detail in grade 8. I'm sure you started that in grade 7 as well, grade 7, 8, 9, and 10, right? But exponential equations, the variable, the unknown variable, is in the exponent, hence why it's called exponential equations, right? So again, we're looking at a very interesting question. So let me just start from the top. Question 1, we are required to solve for x, right? So let's say we have this equation. I have 2 raised to the power of x plus 1 plus 2 raised to the power of x plus 2 is equal to 6. Right, very, very interesting. Okay, now the goal to solve exponential equations is that we need to get common bases. Now in grade 12, you look at something called the logarithm, the log, and how to solve exponential equations for the unknown exponent, right? When the bases are not the same, then you use the logarithm, the log. There's a lot of log rules and stuff, but that is for grade 12. But now in grade 11, our main objective is to get common bases, and we're going to try to use a lot of laws of exponents and the laws of surds to help us do that. And also, I can see a plus here, so we need to also use factorization. There's four ways we can factorize, right? We can take out the highest common factor or at least a common factor. We can, but of course, if they ask you to factorize fully, then you need to take out the highest common factor. So just bear that in mind. The difference of two squares, factorize in the difference of two squares, factorize in by grouping, factorization of the trinomial in the standard form of ax squared plus bx plus c. And of course, in grade 10, you learned about factorization of the sum and difference of two cubes. Again, you need to know all your factorization quite well. But back to this interesting equation, right? I like to factorize by taking out the common factor. But step number one is that I have 2 raised to the power of x plus 2. I can actually split that as two expressions that are being multiplied to each other. How can I do that? It's going to be 2 raised to the power of x times 2 raised to the power of 1. Recall the first law of exponents. How will I simplify this? I'm multiplying and the bases are the same. So the common base is 2 raised to the power of x plus 1. Plus, I'm going to do the same for 2 raised to the power of x plus 2, which is 2 raised to the power of x times 2 raised to the power of 2 is equal to 6. Now I have a binomial on the left hand side of this equation. What can I do? I can take out the common factor. What's the common factor between these two? It's 2 raised to the power of x and 2 raised to the power of x. I know what you're saying. You're saying the highest common factor should be 2 raised to the power of x times 2 raised to the power of 1. Between 2 raised to the power of 1 and 2 raised to the power of 2, you take the exponent, the smaller exponent of the two, which is of course 1. But in this example, again, the instruction is not to simply factorize fully. I just want to solve this equation. So what am I going to do? I'll just take out, let's just make our lives a bit easier. Let's just take out 2 raised to the power of x, because that's the problem, because it has the x, right? So I'm going to take this first term, I'm going to divide it by the common factor. I'm left with 2 raised to the power of 1, plus I'm going to take the second term, which is 2 raised to the power of x times 2 squared. I'm going to divide it by the common factor of 2 raised to the power of x, and I'm left with 2 squared. It's equal to 6. So I have 2 raised to the power of x times 2 plus 4 is 6, right? And now how do I solve this equation? I divide both sides by 6. So 6 divided by 6 is 1, and 6 divided by 6 on the right hand side is also 1. So I'm left with 2 raised to the power of x is equal to 1. And this is a very common question that we see. Now you might say, okay, do we need to use logarithm because the bases are not the same? No, think about the laws of exponents. Any number except for 0 raised to the power of 0 is equal to 1. So how can I rewrite 1 such that it has a base, a numerical base of 2? Yes, I can rewrite it as 2 raised to the power of 0. So I have 2 raised to the power of x is equal to 2 raised to the power of 0. And because the bases are the same, it implies that the exponents will have to be the same as well. So my final answer, it implies that x is equal to 0. And that is my final answer. Okay. Let's look at one more example, right? And then we can call it a day. But again, please try to attempt this on yourself, and then we can mark that together. But let's look at the last example for today, and then you can practice as many questions as you can, because the only way you can get confident to answer a maths question or a maths paper is to do as many questions as you can as practice, and I think that is extremely helpful. Okay, so let's look into it. All right, let's look at question 2. I am required to just solve 4x. Right? Oh, actually, I know I'm jumping the gun, but there's just one more example I would like to do on Surds equations, which is absolutely fun. So let's do this question, and then, so this is the penultimate question, the second last question that we will discuss. We have 3 raised to the power of x plus 3 times 3 raised to the power of negative x minus 4 is equal to 0. Okay, so let's try to solve, or let's solve this equation. Okay, now the first thing, a lot of learners panic when they see a negative exponent, right? But again, we know how to deal with a negative exponent. We can rewrite it as a positive exponent. What's 3 raised? Let's look at the side. 3 raised to the power of negative x. How can I rewrite that such that we have a positive exponent of x. It'll be 1 over 3 raised to the power of positive x. But now we have 3 over 1 times 1 over 3 raised to the power of x. How do we multiply fractions? Top of the top, bottom of the bottom. So what do we have? We have 3 raised to the power of x plus 3 over 3 raised to the power, sorry, we have 3 over 3 raised to the power of x minus 4 is equal to 0. Okay. Now, if this starts to look a bit complicated, right, because we have 3 raised to the power of x, let's deal with something that we are familiar with, right? So what we can do is we can introduce something called k substitution. Because we're dealing with a lot of complicated variables, we can substitute, right, 3 raised to the power of x as k. And you might say, why k from all the letters in the English language? Why k? Because k is rarely used. The most common variable in maths is, of course, x, as we are doing solving for x. It's also a, b, and c, and the rest. So k is just a very odd uh, unknown. So we just say let the unknown be equal to k. So now whenever I see 3 raised to the power of x or 3 raised to the exponent as x, I'm going to substitute it for k. So I have k plus 3 over k minus 4 is equal to 0. That's something we can work with. That's something we looked at in grade 10 as well. Now let's try to get rid of this. Let's try to get rid of this denominator of k, because whenever I see a fraction, I want to get rid of the denominator. So let's multiply the left hand side of the equation and the right hand side of the equation by the LCD, that is k. So I'm going to multiply the left hand side of the equation by k and the right hand side of the equation by k. Whatever I do to one side of the equation, I have to do to the right hand side as well. But remember, when we multiply this trinomial by k, we apply the distributive property. So in a way, k is being multiplied to every single term on the left hand side and every single term on the right hand side, which happens to be 0. So 0 times k is 0. So we don't have to stress too much about that. K times k, we have k squared. Now, the reason why we multiplied everything by the LCD, both the left-hand side and the right-hand side, is to get rid of that k. So the k is divided off to 1. 1 times 3 is 3 minus negative 4 times k is negative 4k. 0 times k, as we said, is 0. Now, let's write this in the standard form of ax squared plus bx plus c. So we use our commutative property. We change the order. We have k squared minus 4k plus 3 is equal to 0. Now you can see that we have a nice standard form of ax squared plus bx plus c is equal to 0, right? So we have it in the standard form. Okay. Now what I'm going to do is I'm going to use the window method as I explained earlier. So I'm not going to spend too much time on this because I already discussed how to use the window method. But just a reminder, we have k squared on top of the first window. We have 3, the constant on top of the second window, and we have the middle term, which is negative 4k at the bottom. So again, we're going to be very deliberate on how we choose our factors. K times k gives me k squared. I have 3 and 1, but of course there's a negative sign here, so both has to be negative. So now when I cross multiply, let's test it. I have negative 3 times k, which is negative 3k, and I have negative 1 times k, which is negative 1k. Then you add these two together. Negative 3k plus negative 1k. So that's the same thing as saying negative 3k minus 1k, which gives you the middle term of 4k. And again, we choose our factors horizontally. So my first factor would be k minus 3 times, and my second factor is k minus 1. K minus 1 is equal to 0. And now, of course, we multiply these two binomials and it's equal to 0. So we have k minus 3 is equal to 0, or k minus 1 is equal to 0. Because if k minus 1 is 0, then 0 multiplied to this binomial is 0. Or if k minus 1 is 0, then multiply that to k minus 3, it will give you 0. So now my answer is k is equal to 3, or k is equal to 1. Okay. Now I'm going to Now it seems like this is my final answer, but remember we're solving for x. That's what the question asked me for, to solve for x. So I'm going to substitute 3 raised to the power of x. Why? Because That's what we said is equal to x, back to its original form, which is 3 raised to, so k is 3 raised to the power of x. So it's 3 raised to the power of x is equal to 3 raised to the power of 1, or 3 raised to the power of x is equal to 1. So now this implies that x is equal to 1, or x is equal to, sorry, this is not done. We have 3 raised to the power of x. I'm going to be very deliberate. I'm going to rewrite 1 such that the base is 3, which is 3 raised to the power of 0. That implies x is equal to 0. So x is equal to 1, or x is equal to 0. Now what I like to do now is just double check to make sure our work is correct. Let's substitute 1 in the place of x and 0 in the place of x. So let's start off with 1. Let's say x is equal to 1. So I'm using my calculator now. 3 raised to the power of 1 plus 3 raised to the power of 1 times 3 raised to the power of negative 1 minus 4. What does that give me? 0. So the left hand side is equal to the right hand side. So I know that my answer is correct. Please always double check your work, right? So we know that x is equal to 1. And get this up. And let's substitute. Now what happens if x was 0? Let's substitute 0 in the place of x, just to see whether it is correct. So if we have 3 raised to the power of 0 plus 3 times 3 raised to the power of negative 0 minus 4, which is equal to 0. So the left hand side is equal to the right hand side. Now we get to the exciting part, the last question for this video, which is a Surd equation, right? Which is a Surd equation. Okay, let me just look for this question. Okay, let me see if I have it written down. Okay, very exciting stuff. So let's look at the last question for today, right? Okay, now we have to solve a simple Surd equation. Now, when I refer to Surd, of course, it deals with the square root or the third root, etc. But in this case, we are mostly dealing with the square root. So let's get started with this question. Okay, so let's look at this very interesting question that we have, right? We have to solve for x, right? We have we have x minus the square root of x plus 6 is equal to 0. Interesting. Now we have a square root here, and I want to get rid of that square root. So I ask myself, what is the opposite of the square root, right? It's the square. The square and the square root, they are inverse to each other, just like the cube and the cube root, or the fourth, to raise an expression to the power of 4, and the fourth root, or the fifth, and so forth and so on. So I need to use the square root, but first I want to get the square root on its own. I want to isolate it. So I have a binomial on the left hand side of this equation. I'm going to take this second term, and I'm going to take it to the right hand side of the equation. So what do I have? I have x is equal to 0 plus the square root of x plus 6, right? Plus the square root of x plus 6. Now that I have the square root alone, it's much easier to work with. So step number 1, try to get the square root alone and try to isolate it. How do I get rid of it? I need to square root. I need to square the square root of x minus 6. Whatever I do to one side of the equation, I have to do to the other side of the equation as well. So what am I left with? I'm left with the x squared is equal to the square root and the square, they undo each other. So that is x plus 6. Right now I can get all my variables to one side of the equation. I can see I might have to factorize a trinomial in standard form of ax squared plus bx plus c, which we did in the previous examples as well. So when I take x to the other side, it becomes negative x minus 6 is equal to 0. And now we factorize this trinomial. So x times x gives me x squared, and 3 times 2 gives me 6, but of course this is negative 6, so let's be deliberate. The sum needs to give me negative 1. So let's say negative 3 times 2 is negative 6. When I cross multiply, negative 3 times x is negative 3x, and 2 times x is plus 2x. So my factors are x minus 3 is equal to 0. X minus 3 times x plus 2 is equal to 0. Now I can solve this equation. It's going to be x minus 3 is equal to 0, or x plus 2 is equal to 0. So x is equal to 3, or x is equal to negative 2. Now, just think about something for a minute. The square root of a negative value. The square root of a negative value, let's say for example, we have negative a, whatever that a value is, it is non-defined. It's actually an imaginary number, right? Which we learn in further maths or when you study maths at university, right? So what we need to do whenever you have a square root, you need to check. You need to do a check whether the left-hand side is in fact equal to the right-hand side. So let's look at the left-hand side. Let's say x is equal to negative 3. So I'm going to substitute, sorry, let's say x is equal to 3. I'm going to substitute 3 in the place of x. So I have 3 minus the square root of 3 plus 6. What does that give me? 0. So the left hand side is equal to 0, the right hand side is equal to 0. So yes, x can be equal to 3. But let's try x is equal to negative 2. Let's substitute negative 2 in the place of x. Minus negative 2 minus the square root of negative 2 plus 6. What does that give me? That gives me negative 4. So sometimes, of course, it could be the result of a non-real number, or sometimes it may just not work, as in this case here. So I have negative 4 on the left-hand side of the expression. So that gives me the left-hand side of the expression when x is equal to negative 2 is negative 4. The right-hand side of the equation, what is that equal to? 0. So the left-hand side is not equal to the right-hand side. Therefore, this is not applicable. X cannot be equal to negative 2. So what is my final answer? X cannot be equal to negative 2. So what's my final answer? Is that therefore x is equal to 3 only. So I like the examiner to know clearly that I'm rejecting negative 2 as a solution of x, that x is equal to 3 only. So when you solve a Surd equation, it's extremely important. It's not that if you have some spare time, just double check your work to make sure it's correct. No, you have to confirm whether or not that value of x is acceptable, because you're rushing in the exam, you're solving for x, you're saying, cool, that's good, I have values for x, but actually you're losing a mark when you say that x is equal to negative 2, because it is not. So you have to confirm to see whether the left hand side of the equation is equal to the right hand side. And generally as well, it's good practice in any equation just to confirm whether your work is correct or not. But that is some of the examples and some of the questions that I found to be quite interesting, and I wanted to practice with you as well. So make sure you go through as many exam focused questions, a lot of past papers, whether it's DBE or IEP papers. It will help you and make you more confident to answer these questions. So that basically wraps up this lesson. Grade 10s, grade 11s rather, I wish you all the best, and I will see you in the next video.